Welcome back! Last time we left off with an MCP4822 and an MCP4922 DAC producing some really nice sine waves using some freely available libraries for the Arduino. If you haven't watched the first video yet, card link, you should probably do so now before watching this video, because the basics I cover in that first video, I will not repeat them in this one. This time I want to delve in even deeper. I intend to drive these DACs without any library, okay? Because the two libraries I introduced you in the first part, they are only able to drive 5 chips out of the big 12-chip family of MCP48, MCP49 DACs. So yeah, I want to cover all the DACs of the family. And I want to try if I can get a little bit more performance, that is transactions per second, or yeah, value changes per second out of these things using an Arduino. Furthermore, we have to talk about output filtering for these DACs. I totally skipped that in the first part of the video. And I want to show you some, well, maybe not straightforward ways to use these DACs. Yeah, some tricks that are mentioned in the datasheet, other stuff, yeah, that came to my mind. So this video will probably get a little bit longer than the first one, so feel free to use the time index below in the description to jump to the parts that you are interested in. Enjoy! Let's get started and drive these things directly. This is all the text you will find about their serial interface in any of their datasheets, and it's the same for all 12 members of the MCP48, MCP49 family. So we're dealing, we already know that, with a serial peripheral interface, SPI, and that interface supports the modes 00 and 11. We don't need to know the specifics there. The SPI library of the Arduino will take care of that. This paragraph under write command tells us everything we need to know. Okay, initiate by driving the CS pin low, followed by clocking the 4 configuration bits and the 12 data bits into the SDI pin on the rising edge of the serial clock. Yeah, again, the SPI library of the Arduino will take care of that. The SPI pin is then raised, causing the data to be latched into the selected DAC input registers. Looking at the block diagram, which is also very similar, we saw that in the first part for all members of the family, we have our SPI interface here, and we pull the chip select low and somehow clock in 16 bits, yeah, for configuration and 12 data, and they somehow land in one or the other input register. If we have a squiz at the SPI timing diagrams of, yeah, at least 6 members of the family, they all look the same. The details don't matter at that point. They're all the same, and I can assure you they're also the same for the other 6 members of the family. So you have to clock in 16 bits, and that will write one input register or one channel. So what are the differences between the 12 DACs then? And for that we have to have a look at their registers. Let's start with the data portion of the registers, which I have marked yellow here. So the 12-bit DACs from the family use all 12 bits, the 10-bit DACs only 10 bits, yeah, ignoring the last 2, and the 8-bit DACs, well, 8-bit ignoring the last 4. The 4 config bits, which I marked green here, are basically the same for all members of the family. It's just some types either ignore a bit or the use of a bit is restricted. So the first bit determines if you're writing to the A or the B channel. If you have a single channel DAC, this always has to be 0. The buff bit determines if the input buffer for an external voltage reference is bypassed or not. That bit is only used by the MCP49s, which require an external voltage reference, and is completely ignored by the MCP48s, which have an internal voltage reference. The gain bit, determining the gain of your output amplifier of 1 or 2, is used by all types, as is the shutdown bit, which determines if your output pin is shut down or active. And that's how that whole bit dance looks on the scope. And I'm probing the MCP4922, still using the library for it. Let's zoom in. At the bottom we have our chip select signal, which goes low each time we have a data transmission of 16 bits. And that grizzle is just a bit crosstalk here from the, in the middle, the serial clock. So this should be 16 clock cycles here. So that library is sending byte by byte, so 8 clock cycles each. And at the top we have the master out slave in signal. Let's zoom in at the first data package. So again, chip select is low, and we have here 8 clock cycles for the first byte, another 8 clock cycles for a second byte, a total of 16 bit. And please note that the first bit here, that's low in this data package. Let's move to the next one. I have to turn quite a bit to get there. You see chip select is going high again, chip select is going low again, and here we go. And you see for that next 16-bit data package, the first bit is high. And you remember the first bit was the channel selection. And I'm driving here a dual channel DAC, and the library is writing, alternatively, the value for channel 1 and channel 2. So first bit is alternating between high and low in each data package. And when we try to drive the chip ourselves, we should see exactly the same. And there are the according sine waves on the outputs again. But if you have a closer look, they are now 48 Hertz. And that is because I'm no longer using the 4922 library, but my own code. And we will have a look at that code now. So the code, as quick as possible. I will only explain the delta to the code I used in part 1, where I utilized some libraries to drive the 4922 and the 4822. So first difference, I'm no longer using libraries, I'm just including the SPI.h. Then I define a new type, which is simply a 16-bit unsigned int, because that's my register format for all MCP48s, 49s. Just for better readability, I define a bunch of constants here for the bits in the register. So bit 1 here, either 0 or 1, controlling if it's channel A or channel B we're writing to. The second bit, 0 or 1, decides if any voltage reference input buffer is on, off. Third bit, if the output gain is 2 or 1. Fourth bit, if the output is on or off. Of course, you cannot use all combinations of bits for all MCP DACs. That's the same, just the pins where my chip select and load DAC pins are connected. And then I define 4 constants, which will contain just the 4 control bits to the left. And I do that for each chip and each channel. So I have 2 chips with 2 channels each, makes 4 constants. And for example here for the MCP4822 channel A, I simply OR together the bits I want. So of course it's channel A and buffer is off because a 4822 has no input buffer for external voltage reference. Gain is 1 and output is on. That's that section here. I still have my array with 512 sign values, and I still initialize that array here in the init part. And then I do a little bit more. I not only have to handle the load DAC pins of both chips on the breadboard, I now, no longer using libraries, have also to take care of the chip select pins. And they go initially high, of course. I don't want to do anything at that point. And I issue, you need to do that, an SPI begin. That simply tells the Arduino SPI library that it can now access the hardware pins, okay, for the SPI bus. In the loop, nothing new here in the outside, so I loop forever and then I loop through all my 512 steps of the sine wave. And I first issue an SPI begin transaction. That's just good practice, and no, that's required, not just good practice. And the SPI settings are maximum of 20 megahertz. We have that from the datasheet. Most significant bit first. You saw bit 15 was to the left and goes in first, goes over first on the bus, and SPI mode is 0. You remember that also from the datasheet. And then here currently I'm writing my data to the MCP4922. That is the first thing I do. I set the chip select line low. Okay, we saw that also in the diagrams and the datasheet. You have to put it on low first, or generally on every SPI device. And then I do an SPI transfer 16, so transferring 16 bits over the SPI bus. And the bits I transfer are, well, my first 4 config bits, which I have in that variable here, or constant. And then the 12-bit sign value, which is, of course, that is aligned to the left. This is aligned naturally to the right. So that's my 16-bit of the register I want to write. And afterwards we have to pull the chip select pin high again, so that the data that is transferred here is really transferred inside the chip into the register. And I do that basically the same for the second channel, and then I do an SPI end transaction. And the stuff commented out here, that is exactly the same just for my MCP4822. And if you have not a 12-bit DAC, but a 10-bit DAC or an 8-bit DAC, all you have to do is shift your sign values for the 10-bit DACs 2 bits to the left. You remember from the datasheet, these 10 bits of the 10-bit DACs were aligned to the left. And for the 8-bit DACs, you have to shift the whole shebang, or the 8 bits you have really valid here in that array, 4 bits to the left. And that's it. That's all the code. So, why is my code generating a 84 Hz sine wave so much faster than using the library which just managed to generate a 70 Hz sine wave? To answer that question, I went back to probing the SPI bus. Looking at the big picture, you see that I can now fit 3 chip select highs on the oscilloscope screen, and I'm using the same timescale as before, 2 microseconds. Comparing that to the library, you see right away that the chip select highs are longer. The chip select lows are also longer, but the chip select highs is where basically nothing happens on the SPI bus. And these longer delays are simply caused by the overhead of calling a method of an object. If we zoom into one of the 16-bit data packages, and my timescale there is as before 200 nanoseconds, you notice that it still consists of 2 bursts of 8-bit each with a little pause in between. But that little pause is actually the Arduino SPI library. You remember my code? I have called it only once to transfer 16 bits. If you compare that to what the MCP4922 library generated, you see that the gap between the 2 8-bit data bursts is longer. And that's the library not making optimal use of the Arduino SPI library. To summarize, libraries, and this is not a library bashing, okay? Kudos to all the people who are writing libraries for the Arduino environment. They are the ones who made the Arduino environment what it is today. With that out of the way, when you use libraries, you have that method call overhead, and that's the unavoidable cost of encapsulation and making your code look nice. And libraries are not necessarily optimized for speed, but they tend to be written to be universal, so you can use them for a lot of use cases. Looking at the performance data, and we used a 16 MHz nano, with the MCP48XX library, we were generating a 62 Hz sine wave on 2 channels. And you remember my sine wave consisted of 512 samples, and this gives us about 63,500 transactions or value updates in the DAC per second. The MCP4922X library delivered a 70 Hz sine wave, and that leads us to 71,700 transactions per second. And without the library, my raw code, we were able to reach 84 Hz. That corresponds to 86,000 transactions. Now onwards to the theoretical limits of the MCP DACs. If you just look at the SPI interface, that can run at 20 MHz and you need 17 clock cycles to get a value change done. 16 SPI clock cycles for the 16 bits and 1 to pull your chip select line high again, at least for a short time. And that would give you a whopping 1,180,000 transactions. But if you look at the settling time of the output amplifier, that's typical 4.5 microseconds. And then you have 222,000 transactions per second left. And that value is given for a quarter to 3/4 full scale, and at the end plus minus half LSB. And if you look at the slew rate of the amplifier, 0.55 volts per microsecond typically, and you divide the internal reference voltage of the MCP's 48s by that slew rate, you get 3.72 microseconds. that leaves you a little bit higher value of 269,000 transactions. However, if you use gain 2 and go up to 4 volts, this value halves, and then you are at 135,000 transactions per second, which is not so far away from these values. And yeah, you get, of course, the 20 megahertz nano every, which would improve all these numbers by 25%. Enough about software. I switched back to the MCP4822 with its built-in voltage reference, so I'm using now the code that was commented out in the main loop, and in turn I commented out the code of the MCP4922, and again, of course, we get some nice sine waves. Or do we? Let's zoom in. We are extremely zoomed in now. So 50 millivolts per division here and 20 microseconds per division here. And at that level, you can see that the digital steps of both our sine waves are not perfectly in sync. In fact, the channel A changes its value a little bit earlier than the channel B. And that's a natural product of how we drive that DAC over SPI. We first send a value for the channel A, and then we send a value for the channel B. And in some application, this little delay between the two channels can ruin your day. And that's where that load DAC pin of the MCP48s and 49 comes in, which I ignored so far. Up to now, we have that constantly pulled low, meaning whenever we load a value via SPI for one of the registers, it directly ended up in the DAC registers and immediately changed our output voltage. But if we keep it high while we are loading new values for both channels and then pull it low, we can synchronize the value changes of both outputs. I modified the software to use the LDAC pin. I mean, we already connected it to the Arduino. And now you can see, the values change at exactly the same time for the A channel and the B channel. And you also see an extreme crosstalk here from the LDAC line. I'll show you on the breadboard in a second. Here's my MCP4822. And here comes the jumper from the Arduino carrying the load DAC signal, to that pin here. And the pin next to that, which goes here to the, let's put that out of the way, to the oscilloscope probe, that's the output of my channel B. So you have here two pieces of copper running parallel for half an inch or 12.7 millimeters. One carrying the analog signal of channel B and one carrying the load DAC digital signal, which gives us just a short pulse every now and then, and so you get crosstalk. And we have a short snippet from the datasheet for that too. Layout consideration. Inductively coupled AC transients and digital switching noises can degrade the output signal integrity, as we have just seen. And furthermore, breadboards and wire wrap boards are not recommended if low noise is desired. Who would have known? Anyway, the changes to the code are minimal. So I initialize in the setup my MCP48 LDAC pin with high. Formerly it was initialized or set to low, like I'm still doing it for the 4922. So no data is flowing from the SPI registers to the actual DAC registers. And I told you I removed the comments here and commented out my 49 stuff. And here we have these two additional lines, okay, where after I loaded both registers with new data, I pull the LDAC line for a short while low and then back up high again. And yeah, that's all the software changed to handle that LDAC pin and to synchronize, yeah, the change of values of both channels in your DAC. Another thing I completely omitted this far is output filter capacitors, like you see here in the typical application. And there's even a chapter 6.3 in the datasheet, at least for the MCP48X types, where it clearly states under output noise consideration, a small bypass capacitor on Vout-X is an effective method to produce a single pole low-pass filter that will reduce this noise. So basically that output capacitor in conjunction with the output impedance of the output amplifier forms an RC filter. And then they go on, but in the end they say the tested range for stability is 0.001 microfarad through 4.7 microfarad. Unfortunately, nothing in the datasheet gives us a hint about what is the output impedance. So we have no way to really calculate these capacitors. So yeah, we will have to experiment a little bit. So I put an 0.1 microfarad capacitor at the channel A output of my 4822, and at the same time in software I switched off the use of that low DAC line. It's now always low again, so we don't see that nasty crosstalk here. Anyway, let's zoom in because, yeah, at a first glance, that capacitor did nothing. And maybe there's a reason they omitted that chapter from the datasheet of the MCP49, because, yeah, that's my yellow channel 1, now output filtered with a 0.1 microfarad capacitor, and it certainly looks worse than my unfiltered channel B. Let's try a smaller capacitor, 0.01 microfarad. So 0.01 microfarad or 10 nanofarad looks not as bad, but our unfiltered output is still better. So let's try getting bigger, 1 microfarad. Nah, things get definitely worse with a 1 microfarad output capacitor. Anyway, let's have a look at the schematics and at the breadboard. And there it is, my 1 microfarad ceramic output capacitor here between my ground rail and my channel A output rail. To make things very clear, here's where I placed that capacitor. So on the Vout A pin to ground, and yeah, not working. Let's just forget about these filter bypass capacitors directly connected to the outputs of the DACs. At least in my application scenario, where there's just an oscilloscope probe with, 10 mega ohms impedance connected, they simply don't work. There might be other application scenarios where they do their job, but somehow I doubt that. There might be a reason that this chapter is completely omitted from the MCP49021222 datasheets. Now that looks much better. Yeah, my filtered channel A and my B channel unfiltered. Looking at the big picture, you can probably guess what I've done. Yeah, so my filtered channel is a little bit attenuated and it got now a little phase shift. And yes, I added an RC filter. Here's my output pin, the row, that's my R, I think 16 kilo ohms, and there's the blob under the oscilloscope probe going to ground, that's my C, 100 nano, and that's an RC filter with a corner frequency of 100 Hertz. And to make things clear in the circuit diagram, so I have that RC filter now here, 16K, 100 nano, so 100 Hertz RC low pass, and my oscilloscope probe is connected here. This simple method has of course its drawbacks. We already saw the signal attenuation, so if you are relying on specific signal levels, it's not for you. Also the phase shift, if you are relying on a defined phase relationship between the A and the B channel, you can't use it either. However, it makes a pretty nice signal, huh? Okay, let's move on. To the question, why are there these MCP49 variants that don't have an internal voltage reference? For that, we have to have a look into the MCP48 datasheet. And there we see that the internal voltage reference won't win any awards. You can do the math yourself, but basically it's a plus minus 1.95% voltage reference. Keep in mind that the least significant bit for the 12-bit DAC types is about 0.025%. That makes that voltage reference a plus minus 80 least significant bit reference. If you wanted a voltage reference that is in the order of magnitude of plus minus 1 least significant bit, or even a little bit better, you would have to take something like that max 6126 with 0.02%. However, these are expensive and these DACs are not. So these MCP49 variants allow you to buy a relatively cheap DAC and then, add a voltage reference. I have here these AZ431As, which are 0.4% to your circuit to achieve the precision you need. At your expense, of course. I switched back in the software to driving the MCP4922 and I added an AZ431A as voltage reference for the chip. And we have very nice sine waves, and maybe even the nicest sine waves we've seen so far. I'm here at my usual zoom for close-ups, 20 microseconds and 50 millivolts per division. And it's not filtered by an RC filter or an output capacitor, but that looks really nice. It definitely looks much nicer than using the 3.3 volt power rail of the Arduino as reference. Looking at the schematic, I've added that voltage reference here, and the AZ431 is a shunt voltage reference. So I have a shunt resistor here with 470 ohms to the 3.3 volt rail of the Arduino. That gives me a current of about 1.5 milliamps or so. And I've added here at the power supply of my current reference an 0.1 microfarad decoupling capacitor. And I use that 2.5 volt rail now to feed the voltage reference inputs of my MCP4922. It's getting a bit crowded here on the breadboard, but anyway, here comes my Arduino 3.3 volt rail, and here is my shunt resistor, and here is my voltage reference going to ground with its reference input bound to the cathode, so fixed 2.5 volts. And here's my 0.1 microfarad decoupling capacitor. And I use the output to feed my two voltage reference inputs. But who said the input voltage here and here has to be a fixed reference voltage? In the input amplifier section of the datasheet, we find these two lines, multiplier mode bandwidth, which are 450 and respectively 400 kilohertz. the 450 for unbuffered VREF inputs and an output gain of 1, and the 400 kilohertz for unbuffered and output gain 2. And this means you can feed analog signals into the VREF inputs, which are then multiplied by the DAC value. And that allows you to create really fancy pictures like that. I'll zoom in. So my channel 1 is the RC filtered sine value from the MCP4822, and I'm feeding that into the reference input of the MCP4922's A channel. And at the same time, I'm changing, obviously at a slower rate, the DAC value of the MCP4922A channel. And obviously I'm using the same sine array to change the DAC value. And what I get is a sine wave modulated with a sine wave. I zoomed in a little bit more here, so my input sine wave, and this is my modulated sine wave. Obviously we are here at the maximum value of the modulation, that is the digital value of 4096 for the DAC. And if I scroll, we're here near the DAC value of 0. Now, when you are asking, Robert, you could do that directly by feeding the appropriate DAC values in here. You are missing 2 points. First, this little sine wave here has still a 12-bit resolution, in that little amplitude range, because that's from an analog input signal. Okay, and second, this is just an example. You have here the possibility to multiply any analog signal with a precision of 12 bits. I mean, you probably heard from variable gain amplifiers, but go out and find one that, gives you a 12-bit range of adjustment. I didn't have to change much on the breadboard. I'm just feeding here the RC filter output, whereas also my channel A oscilloscope probe connected, to the VREF channel A input of my 4922. And second oscilloscope probe is obviously connected to the A output of the 4922. So on the schematic, I'm now feeding here a sine signal into the VREF A input of the MCP4922. And I'm getting that here on the RC filtered output from my MCP4822. So, changes to the code. I changed my MCP4922 channel A register value, the buffer, to off, because the datasheet only gave us a bandwidth for the VREF input for buffer off. I surmise that with buffer on, the bandwidth is abysmal. And the other changes in the main loop, I have another index variable here, and I moved my begin transaction to the very beginning. I'm doing everything in one big SPI transaction for speed reasons. I still have my forever loop, and then I have an additional loop, from 0 to steps in 2 increments. And that's basically my modulation, which I sent via SPI transfer to my MCP4922 channel A. And in the inner loop, that's still the same. I simply sent my 265 sine steps to the MCP4822 channel A. Please note that the modulation frequency, I'm going here through 128 steps, so my modulation frequency is a 128th of the frequency of my base sine wave. That's all. Yeah, I saved that read for the very end. And, well, by now you maybe know not everything about the MCP4849 family of DACs, but most of what's to know about them. And with that, I bid you farewell and say bye.